Welcome everybody. It's a pleasure to have here today Thomas, who accepted to talk at our CosmoVerse series. Thomas is a postdoc at the Laboratoire de Physique Nucléaire and des Hautes Énergies of the CNRS, working on the Jaeger Transient Facility data to develop a new Type Ia light curve fitter to improve the constraints on the dark energy equation of state. Previous to that, Thomas was a postdoc at the University of Hawaii, working on cosmology multi-messenger astronomy, using the all-sky automated survey for supernovae. And before that, he was a postdoc at UC Berkeley, working mainly on Type II supernovae cosmology in the SNe II work. This was also the topic of his PhD thesis that he earned in Chile University. Today, Thomas will present Type II supernovae in the SNe tension. You can start, please, when you're ready.
So thank you, everyone, for being here. And thank you, Eleonora, for the introduction and for the invitation. It's nice to be here and present my work. So I'm pretty sure that everyone have heard about Type Ia cosmology and the discovery of the accelerated expansion of the universe and the Nobel Prize won by Adam Rees, Saul Perlmutter, and Brian Schmidt, but not too much about Type II supernovae. This is mostly because for Type Ia cosmologists, Type II are only contamination on their survey. They act like trash. So here I will show you what we can do with trash. I will show you that you can do nice science and you can derive the Hubble diagram. So as I said, my talk will be on cosmology. So in cosmology, we are interested in some of the greatest questions in astronomy. For example, we want to know what is the future of the universe. So using supernova, you can study the dark energy nature, and you can put some constraint on the universe evolution. You can also measure the age of the universe, so you can measure the expansion rate of the universe using Type IIs. And finally, using supernova. And also, you can also measure how the matter is treated in the universe. So this is mostly what I'm working on, but on this talk, I will focus only on the age of the universe and meaning on the Hubble constant. So if you want to measure age, you need a distance and velocity. So you have the distance and velocity, you can obtain a time. So first, there are different ways to measure distances, and one of the methods is called the distance ladder. So astronomers use the analogy to ladder because to measure the object distances, you need to rely on the previous step and move further and further from the Earth. So the basic idea, if you want to measure the expansion of the universe, you need to measure the distance of galaxy in the Hubble flow. So in the Hubble flow is where the motion of the galaxy is only due to the expansion of the universe. There is no peculiar velocities due to some structure close by. But to reach those galaxies at very distant, you need to start locally using geometrical distances. Then you can use calibrator. And finally, you can reach the last step, the last rung. So here I will give details about the distance later. So as I said, first you need a method to measure close by distances. And one of the best methods is using parallax. So the parallax is based on the motion of the apparent motion of the star around during the year. So for here, you see a yellow dot is the sun. You see the Earth at two different epochs, 6 months later, and the motion of the star, the apparent motion of the star will moving with respect to the other star in the sky, and you can measure this angle, the parallax angle. And from the parallax angle, you can use geometrical methods and easily derive the distance d. So this is what Gaia is doing. I've done measuring millions of parallax with an high precision in the Milky Way. But as you can see, when the distance increases, the parallax angle becomes smaller and smaller. So you cannot measure a very, very distant object. You can only reach some kiloparsec. And there is other geometrical distances for the first rung of the distance later that I don't want to detail here. You have the eclipsing binaries, for example, and you have also the maser in the famous galaxy NGC 4258. So using this method, you can have an absolute distance measurement in the Milky Way and some galaxy close by, like the Large Magellanic Clouds, WM31. And so you have the first rung of the distance slider. Then you want to go further and further. You cannot rule out a ruler to measure distances in the sky, so you need to use what we call standard candle. And this very simple method too is based on the inverse square law. So imagine you have a light here, and you are at a distance of 1. At a distance of 1, you receive a brightness of 1. If you go 2 times further, at a distance of 2, you will receive 1/3. And if you go 1/4, and if you go at a distance of 3, you will receive 1/9. So the flux that you receive on the Earth decrease with the distance, the square distances. So if you know the intrinsic brightness of the object, you can compare this to what you receive on the Earth, and you can measure the distance. This is very simple, but life is not always easy. And so you need to know the intrinsic brightness of the object, and this is the more difficult. And this is what you do every time at night when you are driving. So when driving, when you see the light of the other car, if the lights are bright, your brain knows that the car is close, and if the light is faint, the car should be far. And if you don't know that, please don't drive at night, it can be dangerous. So your brain does that, and it's the easy stuff to do, but you need to do the intrinsic brightness. For example, here, 2 cases, you have a truck, so the lights are very, very bright, but it's far. And if you have a bike with a small light, and it can be close, the light will be fainter. So this means that if you don't know the intrinsic brightness, if you don't know the property of your object, you cannot measure distances. So you need to know perfectly what object is and the magnitude, the intrinsic magnitude. And one of the first objects used to measure distances was the Cepheids. So here you can, Cepheids are precessing stars. Here I show you an example of Cepheids in the M31. So these are images from HST. This you can see the epoch here, and you can see how the brightness evolved with time. So brighter, brighter, and then dimmer, dimmer. And Henrietta Leavitt in 1908, she found a correlation between the brightness, so here, and the period of the pulsation. So brighter Cepheids have a longer period. So you can easily measure the period of the Cepheids, taking images at different epoch, and you can deduce the brightness of the Cepheids, so therefore you can measure distances. So this was in 1908. Since that time, we made a lot of progress, and we observed more and more Cepheids. And here I show you an example from one of the last plots showing the period density relation for Cepheids from Adam Reed's paper in 2019. So you see magnitude versus the period, and you can see that a very nice correlation between the magnitude and the period. And if you go to near-infrared bands, the correlation is even better, or you see less dispersion. So now you have the second rung of the distance slider. First you measure, you use geometric methods like parallax, fixing binaries to calibrate, to measure very well your Cepheids absolute magnitude, and then you can measure the distance of Cepheids in a more distant galaxies up to mostly 40 megaparsec. So now you have everything. So you have all the distance, and as I said previously, when you want to measure a Hubble constant, which is the time, you need also a velocity. So I will not give a lot of detail about this because everyone knows that. To measure velocities, you can use the Doppler effect. So you take a spectrum of a galaxy and you can measure the shift of the line, and we can measure the redshift. I only put this slide because I like to highlight the work from Cypher in 1916, because Hubble then used all this work and never mentioned his work in his famous paper. So I like to highlight what he has done. So now you have the velocities, you have the distances. So therefore now you can build what we call the Hubble diagram, which is a velocity, so measured from Cypher, and the distance measuring by Hubble using Cepheid. I think this must be one of the most famous plots in astronomy. And even if one of the most famous plots in the astronomy, you have some error. So if you look at the unity here, is a kilometer and a kilometer per seconds, but whatever is still one of the best plots in astronomy. So if all the galaxies were moving randomly, so some galaxy will coming toward you, away from you, you should see here a cloud of points. But it's not what you see here. You clearly see a correlation between the distance and the velocity. More distant galaxies are moving faster away from us. And there is not a lot of explanation for this. There is only one explanation, is that the universe is expanding. So this was the first optional discovery of the expansion of the universe in 1929, made by Hubble. But also, I like to mention that 2 years before, Georges Lemaître, also using theoretical analysis, shows that one of the solutions for the relativity general equation was an universe in expansion too. And so from the Hubble diagram, you can measure the Hubble constant, what you call the Hubble constant, which is the expression rate of the universe, H0. So this is what Hubble have done, and also Georges Lemaître. And this was the first value that people found of H0 in around 600, between 500 and 600 kilometers per second per megaparsec. Values, pretty high values, and with a lot of uncertainties, of course, for the epoch. But then you can see an improvement in the measurement of the Hubble constant with a decrease of the error bar. This was due because we found that all the Cepheids are not the same. So among the Cepheids, you have bike and truck. So you need to select only the same class, the same type of Cepheids. And like this, you can improve the measurement of H0. But you are still in a very close by with the Cepheids. You are affected by peculiar velocities. So the idea is to find an object which you can use to measure distance, very, very distant galaxies. So this is one of them, for me, at least, one of the most beautiful images in astronomy from the ultra deep field from the Hubble Space Telescope. I'm pretty sure that we'll have better images soon with the GBST, but for the moment, it's one of my favorites. So here you can see all the dots are not stars, they are all galaxies. You have like more than 5,000 galaxies, I think, here in these small images. This is only a small portion of the sky, like the size of a rice grain, more than this. And as you can see, it's mostly impossible to see stars or Cepheids. You cannot resolve the galaxies. So you cannot use Cepheids to measure very, very high distances. But you can use supernovae. So the supernovae, the first term was named by Zwicky in 1931, and supernova is a stellar explosion that can briefly outshine an entire galaxy. Here I'll show you one of the most famous examples of supernovae. This was a type II supernovae, which exploded in the Large Magnetic Clouds. It's called SM 1987A. A because it was the first of the year, so we don't have a lot of imagination for the name. And you can clearly see the pre-explosion image here, where you can see the arrow, you can see a star, and after you can see a big explosion, something very, very bright. And you can see that the supernovae is much brighter than anything in this galaxy, much brighter than any Cepheids that you can find. So supernovae are very useful in cosmology to derive distances. So then you can put constraints, as I mentioned in the introduction, about the dark energy, dark matter, H0, and also the famous tension between the S tension. And also they're useful for many other fields in astronomy, like stellar evolution or galaxy evolution, etc. So here is one of the, I think, is the most updated Hubble diagram with type Ia supernovae, published by Brute in 2022. So you can see the distance modulus here, the distance, and the redshift. And you have mostly like almost 2,000 supernovae here. So you cannot use all the Hubble diagram to measure H0, because at low redshift, so you are affected by velocities. You can see here the large error bar and distance modulus. and higher redshift, you start to be sensitive to the cosmical parameters. So you only use this part of the diagram between 0.01 in redshift up to 0.15, 0.2, depends. Because you can see that the error bar are much smaller. So now you have the free run to measure the Hubble constant using the type 1a supernovae. Again, you have the geometry distances, you calibrate the Cepheids, then you measure, you calibrate the type 1a supernova, which explode in the same host galaxies than the Cepheids, and then you use those calibrated supernova to measure precisely the distance of supernova in the Hubble flow. So you can fit this, and from this you can measure the Hubble constant. And this is what Adam Ruiz have done with the SHOES team. Then you have a second way to measure the Hubble constant is from the CMB, the cosmical microwave background. So the first kinetic radiation after the Big Bang. So here you can see an image from Planck. You can see some tiny differences in temperature in the CMB. And if you take the power spectrum of the temperature fluctuation, you obtain a plot like this. So this is almost the same than the average audience attention of my presentation. We have some peak when people will understand something, and drop when people start to be tired, or maybe I give too many details. But from the CMB, you got the same plot, it's the same, and each peak, or the portion of the peak, or the ratio of the peak, can give you some constraint on the cosmical parameter. And then, so you can measure the Hubble constant in the early universe using the CMB. And then you need to assume a model, for example, our model, standard LCDM, to extrapolate this value to the local universe and compare with the supernova. So this the evolution of the H0 with the date. So I remember we start here with Hubble, and then with Lemaitre, and we decrease, and now we are here mostly around between 50 and 100 kilometers per second per second. Sorry. So everything looks nice. We did a lot of improvement with time. Now we have tiny error bar, so we should be happy, but not, because if you zoom here, now you see a big problem, what we call the Hubble limit tension. So this is in blue. You have the value from the local universe using the type 1a supernova and the distance later by mostly the SHOES team, so Adam Ruiz team. And in red, you see the value using the CMB and using Planck mostly in the end. And you can see now, you see a big difference of more than 5 sigma. So this is not the last value of the SHOES team. So yeah, you have now you have around 5 sigma difference. So this is a big problem. So this maybe the solution of this tension is to change our model, so lambda CDM model, because as I remember, the value from Planck is you need to extrapolate the value from the CMB to the local universe, assuming a model, cosmical model. So if the value differ, maybe our model is wrong. So there are different ways to understand if this tension is real or not. The first one is, of course, to work on those two methods and look at the systematic error and trying to find if there is an issue, maybe with the Cepheid calibration or other. All the other methods is to use independent method with different systematic errors and try to see if we also found or not a tension. And this is what I propose with the type 2. So with the type 2, instead of to use the type 1a for the second and the first rung of the distance later, I will use type 2. This is the goal of the paper mostly, and what my work I show you here. So type 2 supernovae. So you have different classes of supernovae, mostly type 1a and type 2. This is dependent of the presence or not of hydrogen in the spectrum. Yeah. And then for type 1a, you have different classification, but not very important. And so here I'll show you only an example of a nice spectrum of a type 2 supernovae. You can clearly see H alpha, H beta, so hydrogen line, while for the others supernova, you don't see hydrogen. So you can easily classify type 2 and type 1a based on the spectrum. So why we want to use type 2s? Because first, they are the most abundant type of supernova in the limited volume. So you have twice more type 2s than type 1a in limited volume, not limited. This means that you can build a nice sample of type 2. If you do a survey, you will find type 2s in your survey. So you will have data additionally to the type 1a, so you can use them to do science. And I think the most important reason is that we understood their progenitor and environment much better than the type 1a. So for type 1a, we're not sure about the progenitor, but for type 2, we are very sure, because we have pre-explosion images of the progenitor. So here I'll show you one of nice images from Matilda 2010. You can see an image, a pre-explosion. So here you have the arrow which help you to where you need to look at. So you can see a orange star here. Suddenly you have an explosion, a supernovae, which was called 2000 BK, 8 BK, sorry. And then you look at the same place almost more than 3 years after, and you can clearly see that you don't see any orange dots. So then you come back to the pre-explosion images. So you're pretty sure that this star was the progenitor of the supernova. You can measure the densities, mass, and etc., the properties of the stars. And you can put constraint on the progenitor of the type 2. So now we know that progenitor of type 2s are core collapse, red supergiant core collapse, and the mass of the progenitor is between 8 to 15 solar masses. You can see here from the work from David. We don't have only one example of pre-explosion images of type 2 explosion, but we have 1,000 of explosion. So we have good constraint on the progenitor of type 2s. And this allows us to do relative process modeling. And with this method, you can estimate the Hubble constant without any needs of calibrators. I will show these methods at the end of my talk, because this is mostly a new method. So the comparison between type 1 and type 2s, of course, the type 1a are much more luminous than type 1. Type 1a are much luminous than type 2s. So it's more difficult to find type 2s because all the surveys are magnitude limited, generally. But the luminosity of type 2s is enough to find them up to redshift of 0.4. So they are enough to measure the Hubble constant. No need to reach higher redshift. So you can use them to measure the Hubble constant. As I said, for type 1a, we don't know the progenitor, single, double degenerate scenario. While for type 2, we know the progenitor. So this is, we can put constraint, and this can be helpful to understand better the type 2s, and which will allow us to standardize them better. I think also a nice stuff is environment. So all the Cepheids are found in spiral galaxy, of course, and type 1 supernova can be found in spiral and elliptical galaxy. So between the second and the third rung of the distance later, when you use type 1 supernovae, you don't have the same environment between the second rung and the third rung. While for the type 2, they are all in spiral galaxy, so the Cepheids and the type 2 have the same environment. And this is important because one or maybe was the explanation of the difference between Planck and the Schultz team is maybe the use of Cepheids as calibrator. So one of the team from Friedman used the TRGBs, another calibrator, and they find the value between Planck and Adam Ruiz. So this is nice to have calibrators and supernova in the same environment, so you can study if the environment is an issue or not. But yeah, the big question is, are the type 2 standard candle? So here you can see the absolute magnitude in the V band versus the time. So you can see how the light evolve with time. This is more than 100 type 2 light curve from the paper from Anderson et al. 2014. And you can see the big range in magnitude, almost 3 magnitude of dispersion, So here you have like truck, car, bike, you have everything. So you cannot use them to measure distances. And also you have different shapes. So some are more plateau and some are less more linear, which is important to calibrate them. So in type 2 supernovae, you have what we call the plateau phase. And this is important because it's the month where we will be, is the time with the epoch when we will apply all the method. So the type 2 supernova are mostly made by hydrogen. So you have a shell of neutral hydrogen, which is transparent. You have the photosphere where the photon escape. And you have inner region, which is opaque with ionized hydrogen. So the photosphere is at where the atoms start to recombine. So it's around the 5,000 Kelvin. So as the star expands, so with time, the photosphere will move inward and will always be at the same temperature, and the radius will also remain more or less constant. So the luminosity will remain constant. So you are in a case of luminosity here, and then you have a decrease because it start to cool, and when we reach the temperature of around 5,000 Kelvin, when the atoms start to recombine, we will see a plateau phase until the drop and the radiative tail. So how we can calibrate the type 2 supernova, because as I've shown, they are not standard candle. So imagine you have two supernova, one faint here and one bright supernova. So you know that the photosphere is always around the 5,000 Kelvin, the temperature of the hydrogen recombination. So the temperature is the same. So if the luminosity is smaller, it means that the radius is smaller. So the photosphere for the faint type 2 will be at smaller radius than the one for the bright supernova. And because we are in a homologous expansion, the velocity of the ejecta is directly related to the size, to the radius of the photosphere. So faint supernovae will have smaller radius, so lower velocity. So if you can measure the velocity of your ejecta, you can know which supernova is fainter or brighter, and you can make them standard candle. So to measure the velocity, we use different line, or the hydrogen line or the iron line. But in supernova spectrum, you can see a SNe profile in the line. So it's something like that. So here you see an example. So the observer is on the left. You have some dust between the observer and the photosphere. And because you have a dust between the photosphere and the observer, you will see an absorption. You see a SNe profile. And because the photosphere will be moving toward the center of the ejecta, the velocity will start to decrease and the absorption will move to the right. So you can see here how the velocity decrease with time. So you can measure the velocity of the ejecta at different epochs by just measuring the absorption of the SNe profile. And people have done that. So this was Mario Ami and Pinto in 2002. They measure the velocity using the iron line, so 5169 for different type 2 supernovae. And you can see here a very nice correlation between the brightness. So here, brighter supernovae have faster ejecta velocity. So again, you measure the expansion velocity, you can deduce and you can calibrate your supernova. And this is nice because from an empirical correlation, you have also something very similar from the theory. So this is a work done by Kassen and Woosley in 2009, where they use models of type 2 supernovae. They have different energy, so this is the different colors, different mass with the size of circle, and different metallicity, circle and square. But what you need to take from this figure is, again, so you have the absolute magnitude at 50 days, so again, during the plateau phase, and the expansion velocity. And you can see clearly the same correlation seen in the observation, where luminous, brighter type 2 supernovae will have a faster expression velocity. So this is nice. We have everything. And this method is called the standard candle method. So first you correct, as I said, by using this correlation, more supernova have faster ejecta. And as a for type Ia supernovae, you can add another correction, a color correction term, to take into account the dust extinction, etc., where you have brighter supernovae, which in general are bluer. So with the dust correction, you can calibrate your type, you can make your type 2 supernova standard candle. So from a dispersion of a big dispersion that we have seen at the beginning of the plot with all the Likert, you can reduce all the dispersion and you can measure accurate distances. This is I show here the Hubble diagram. So using type 2, a program that we published 2 years ago, you can see so different distance modulus, the distance versus the redshift. And this is the residual of the Hubble diagram. We have like 70 objects here. Then I will show you one with 89, so it's not the most updated Hubble diagram. Different surveys, CSP, SDSS, dark energy, SNLS, etc. But the most important number here is interesting dispersion that we found, 0.27 imagine. This is mean that you can derive distances with a precision of 10–14% in distances. And these are all the people that have worked in type 2 supernovae using the standard method. So you see there are not a lot of people. This is nice because you can again obtain easily the data from other team because I don't use type 2. So this is nice. You can build a nice sample. So this is what we have done. And so then we have the two last rung of the distance later. So we have Cepheid and TRGBs to measure type 2s, to calibrate type 2s, and then we have the type 2s in the Hubble flow. So here in this work, we use 13 calibrators, and we were able to derive a Hubble constant of 75 plus minus 4, a value in tension with Planck again. And because I only changed type 2s, type Ia by type 2s in distance later, and I found the tension, this means that the type Ia are not the source of the Hubble tension. Maybe the Cepheid service, but not the type Ia. And also you can look at the systematic error from this work. So what I've done to estimate the systematic, I use my fiducial models with 30 calibrators and all the supernovae, and I make some variants. So for example, I use a smaller sample, I remove a survey, I do a bootstrapping for the calibrator, so I remove some calibrator and so on, and I find a dispersion, a standard deviation of 1.5 km per second per megaparsec. So now to end my talk, I will show you another methods. This is very interesting because you can measure the Hubble constant without any calibrators, no TRGBs, no Cepheids. So this method starts many years ago, and it's called the expanding photosphere method, EPM. It was developed by Kirchner and Kawan in 1974, so it's very old. But now he has a new revival, and it looks very interesting. I will show you why. Oh, sorry. So the basic idea of the photosphere, the EPM, is to measure a photospheric angular radius and a physical photospheric radius. So you have theta and you have R, so you can easily derive D if you have those two values. So you see, the basic idea is very, very easy. It's very a simple idea. But you need to do some assumption. Sorry. So first, you assume that the ejecta is spherical, and this is a good assumption because if you do some polarimetric study of the type 2 supernovae, you find that the degree of polarimetry during the phase of the plateau phase is only 0.1 mostly, and it increases after when you reach relative tail. But during the plateau phase, the ejecta is mostly spherical, so it's good approximation. Then, as I mentioned previously, you are in homologous expansion. So the radius at any time depends on the initial radius and the velocity of your expansion. Because the ejecta expands so quickly, the radius at any epoch will be much larger than the initial radius. So you can neglect the initial radius. Then you need to do a big assumption is that the photosphere radiates at the black body. So you can write the luminosity and with the Planck function. Here I add also a term to take into account the extinction, the dust extinction. And this is what you obtain on the Earth. It depends on the flux you observe on the Earth. It depends on the distances. So you can rewrite theta equal RD using those two equations, and you end with this equation. Then the radius, you can use the equation of the homologous radius to rewrite the radius. And finally, you obtain this equation where you have the theta over V, T, D plus T0. So if you plot theta over D versus the time, as the slope of this figure will be the distance, and the T0 will be the intercept will be the time of the explosion. And the T, so the temperature, you can obtain temperature using the photometry. So using the color of supernova, you can measure the temperature. And the velocity, as I showed you previously, you can use a spectroscopy and measure the iron line or whatever line, not whatever, but iron line or H beta line. So people have done that from first Brian Schmidt in '94. You can see that this plot, so you have the time and the theta over V. You can see a nice correlation between the two quantities. So you can fit using a slope and the linear fit, and the slope is the distance. So Brian Schmidt, before being famous in type 1a, had done a lot of work in type 2, and he applied the EPM to many supernovae, type 2 supernovae, and built a Hubble diagram. So here's the inverse that I showed previously, but you have velocity versus the distance, and he found a value of 73 plus minus 9 km per second per meter per sec, which was pretty good. So this is a fit in black. But you have a lot of issues with the EPM. First, the supernova radiation is not a black body. If you look at the position of the photosphere, the radius of the photosphere is bigger than the radius where the black body emissions come from. And if you look at, for example, here at type 2 spectral simulation and the black body fit using the color of the supernova, you can see also a disagreement between the black body fit and the supernova, and mostly at in the UV, blue UV part of the spectrum. So the photosphere radiates more as a diluted black body. So to take into account this, people have add in the formula what we call a dilution factor. But this doesn't solve all the problem, because if you look at the dilution factor, the distance measured using the EPM depends on the dilution factor. So here's a work from Jones 2009. You can see two different dilution factors from two different models, from Dessart 2005 and Eastman in 1996. So you see the evolution of the dilution factor versus the temperature, and you can see difference between the two work. And this is very, if you apply those dilution factor and try to do the Hubble constant, this is getting worse. So here is a two Hubble diagram using the EPM, so the distance versus the redshift, velocity, using on the top the Eastman dilution factor, and the bottom the Dessart dilution factor. And you can see that a big difference in the Hubble constant. We find mostly 100 km per second per meter per sec, and the other is 66. So a large difference with error bar not so large, so it's not consistent both values. So you cannot use the EPM like this to measure the Hubble constant, because depending on the dilution factor you will use, you will find a totally different value. So we are lucky because recently we find another way to, so instead of to avoid to use the dilution factor, what you can do is to do spectral fitting. So the first method was developed by Baron and then was developed also by Luc Dessart. The issue with the first generation of the spectral fitting. It was very computing time consuming. In 15 years, we have only 2 or 3 examples of supernovae with spectral fitting. And so it's not easy to apply this to a sample of type 2. But recently, Christian Vogt, in 2020, have created an emulator based on the relative process modeling, which can predict a type 2 supernova much faster. So you can apply for a lot of supernovae. And here I show you an example of how it's work. So in black, you have the type 2 supernovae, 99 EM, one of the most famous type 2 supernovae. And in blue, you have the fit from the emulator. So from the fit, you can obtain what you need: metallicity, viscosity, and temperature. So then you can apply the EPM without the need of addition factor. You need some critical observer for this. You need a good time of explosion. So plus or minus 2 days of instantaneous, because if you have more instantaneous in time explosion, you will have larger instantaneous in the distance, like maybe 10–15% or more. You need a good coverage in a spectral coverage. You need at least 3 to 5 spectra at least, which is difficult to obtain generally. And you need also optical photometry, because you need to flux calibrate your spectra. So you need a photometry to do that, optical photometry to do that. But then when you have everything, you can apply the method. So here's an example of one supernova, one type 2 supernovae. You can see there are 3 spectra at 3 different epochs. So you can see always in black the observed spectra, and in blue the model, the fit. And you can see also you can obtain also the extinction from also the total extinction here. So then you can apply the EPM, so you can calculate the theta divided by V over the time. Here you have 3 points, not so big, and you can do a fit of this, and you can measure the distance. This is what you can find a nice distance, and this is so you obtain a distance without any calibration. So from this you can derive directly the Hubble constant. I want to before to show the 2 last slide, I want to mention this work. So they use the method developed by Christian Vogt, sorry. What they did, they used Sibling type 2 supernovae, so 2 supernovae which explode in the same host galaxy, so they should have the same distance. So this is nice to test the method. So they applied the method to both supernovae. So you have theta over V and the time for the 2 objects on bottom and on top and bottom. And you can see that the values are derived for the distances. So for the first one, 15.06, and second one, 14.95, which are very in good agreements. So the methods looks very nice, it's consistent. So I think it will be a very nice for the future. So Christian Vogt in his PhD thesis, so the paper I have not published yet, they use that method to measure 6 distance of type 2 supernova, and that derives the Hubble constant. So you can see the probability density of the 6 value and the average, and they find a very nice value of 72.3 plus or minus 3 km per second per megaparsec. So the value is also in tension with the Planck value, and again this is without any calibrator, so no issue with TRGBs, Cepheids, or environment or whatever. The only big issue for this work for the moment is that from the 6 supernovae I use, there are 4 at low redshifts that can be affected by peculiarities. So I know that Christian Vogt is part of a collaboration called Ad Hoc, and they plan, and I think they have already data. They will observe type 2s, and they have data for type 2s in the Hubble flow, so more around this part and at higher redshift, and they will apply the method at that time. So I think we will have soon a much better value and a more reliable value, not affected by peculiarities. So thank you, and to conclude, I show you a summary of all the Hubble constant derived using type 2s. So for comparison, you have in orange, you have the Planck value. In black, you have the value obtained by the Schuss team and the Cepheids. in black you have also the value from Friedman and the TRGBs and type Ia. In red, you have the value obtained using the standard candle method. So the last values that we published last year using 13 calibrators, which is consistent with type Ia values and intention with Planck at 2 sigma. You have the value from the EPM, the first generation of EPM, where you can see that you go mostly everywhere because it depends on the emission factor you use. So it's not very reliable. And then you have the last value I show you from Christian Vogt from the telluride EPM, when you do relative process modeling of the spectrum to get the parameter of interest. Thank you very much for your attention.
Thank you so much. Thank you for the very interesting talk. Do you have any questions? Yes, Leandros?
Yes, thank you for the nice talk. Just a question about the standardization of the type 2 supernova. You mentioned that one can use the color and the velocity to standardize the type 2. Is there any information one can extract from the light curve? I mean, I know it's not the same as type 1, but at least is it possible to get some information about the standardization?
Yeah, so yeah, thank you for asking, because I have a slide to answer. No, so this is one of the methods that I show you. And there is another method that I developed during my thesis. This is called the PCM, so the photometric color method, and is use the light curve. So here you can see the type 2 light curve. I don't know if you know the Petit Prince, the famous book in France. This is a draw from this book. So as a type 2 light curve, so you see a decline. And then you arrived, when the electrons start to recombine, you arrive in the plateau phase, yeah? So it will be constant, more or less constant. This is, from this graph, is what we call S2, yeah, slope 2. And when you look at the correlation between the slope and magnitude, you find the correlation. So this is a S2 slope, so the plateau slope, and the absolute magnitude. And you can see that brighter supernovae have steeper plateau. So you can, instead of to use the velocity, you can use the color to calibrate the type 2 supernovae. So this will be very interesting for the next generation of survey, like LSST, for example, for the Rubin. So this is one of the diagram I published. You can also, of course, increase the number of supernova because you need the spectrum. And you can go to higher redshift because you don't need the spectrum. But you see that the dispersion increases to almost 0.4. So your uncertainties in the distance is not as good as a SCM. But I have heard that someone is working with the ZTF data, trying to apply like a kind of this method. They use the slope plus other stuff, and they find a dispersion much better. They find a dispersion of 0.32. So I don't know the paper. I know that some people are working on that. I think the paper maybe will be in the archive this year. So stay tuned. Because, yeah, but yes, there is maybe other way to make them standard.
I see. Okay, thank you.
Shahin?
Thank you so much for the nice talk. Actually, this method using type 2 supernovae reminded me of Holy Cow and TD Cosmo and strong lensing. So I was just curious to know if in the Holy Cow results with the 6 strong lenses, they find some sliding feature for H0, namely if you measure H0 using higher redshift lenses, you find a lower value for H0. That's what Holy Cow that reports. Do you see a similar feature, or do you, so can you show again that?
So first, not only for type 2s, but actually for type 1a, you don't use all the objects you use. Sorry, use only one part of because here you are affected by Velocities and here you are affected by the cosmology. So you use only a part of the Hubble diagram. And Okay, so this was an example. And then if you look at the table, so this is thematic. So this is a cut. For example, in my fiducial models, I use all the supernova from 0.01, and up to maybe 0.3, maybe. So this is the value I obtain for H0. And then I do some cut. For example, here, instead of to use 0.01, I cut at 0.023. This is the value that Adam Rees used in this shoes paper. And you see that maybe you see some differences, but because the bar are plus or minus 4, it's still consistent. And this is when I include all the Hubble diagram, even the one with the precocities problem, and you can see the value. You see maybe here in percentage, maybe it's easier. You can see how was the percentage change. So, and the issue with type 2 is like we still have a small sample. You know, you don't have a lot of objects, so you cannot do all the cut as type 1A have done. But it's pretty consistent, the value, I feel.
Thanks.
Thank you. Vivian?
Hey, hi. I was curious. I wanted to know. So you mentioned that there were supposed to be many more type 2 supernovae.
Yeah.
Presented results that have only a handful compared to type 1A, like 30 or even only 6 or 7 in the latest case.
Yeah, because
discussion. So is there a fundamental reason, or is it just
there is an important word here when I say the more important is volume. You know, when you do a survey, you're not limited by the volume, but you are limited by the magnitude. And the type 1A supernova are much brighter than type 2s. You have almost too many differences. So if you have a magnitude limited survey, you will observe more type 1A supernova than type 2s.
I see. And then another quick question is, if you were to play devil's advocate, what would you need to do to type 2 supernovae to find 67? Like how, or to say it otherwise, if you you assume 67 is the real number for some reason, what do you learn about type 2 supernovae? Is this could you learn something in terms of systematics, or could you roll out any sort of systematic? Is it possible to make it compatible with 67 at all, or not?
I never tried this. From the distance center, it just doesn't look as You can see the different tests I did from the sample, and even when I look at when I use only the TRGBs, so here, those two lines is the same as the differential models, but here I use Cepheids, and here I use only TRGBs. When I use Cepheids, the value is a little higher than the feature value, and only Cepheid, sorry. And when I use only TRGBs, the value is smaller. But in the both case, I'm far to be consistent with Planck. But again, here we're using only TRGBs. I have only 5 objects and or 7 using Cepheids. But yeah, I don't. It's difficult to be consistent with Planck. But yeah, and I think I would like to mention also something that maybe I didn't mention. Here, I test only the 2 last rung of the translator. So the Cepheids distance modulus that I have are from Adam Rees, for example. So I'm not independent totally with his work. I'm only independent on the last 2 rungs, not of the first rung. Just to mention this thing. I think it's important.
Okay, thank you.
You're welcome.
Thank you. Paolo?
Yes, thank you for this very, very interesting talk. I would like to ask you something related to the question of my predecessor. And I have not perfectly understood how many supernova do you have, for instance, inside the 0.05 redshift Z, and if there are many more that could be easily measured in the near future, or they are already there.
Yeah, so I'll try to. So this is a question, mostly the number of objects I have. So
yes, inside. Yes.
So this is mostly inside. So this is between 0.01 to 0.4 mostly. Is the 1, 2, 3. Oh, sorry. others 1, 2, 3. So you have almost 90 here. Okay.
Okay.
And you have 30 calibrators, so 70 RGBs, 7 Cepheid and 5 TRGBs. So this was the first question. Your second question was, so if you want to apply the standard candle method, or if you want to apply the last method I show, the EPM second version, let's call it the tailored EPM, you need a spectrum. So, for example, for LSST, you need we have only the photometry, so you need a follow-up. So you need to take time to get a spectrum. So yeah, so you can have more, but you need to create you need to dedicate time for follow-up.
Okay.
But generally, for example, for ZTF, because people want to work only with type 1A, you need to have a CD machine to classify the supernova. And of course, you don't know what you have. So sometimes you classify type 2s too. So you can maybe also use, for example, ZTF and their spectra, even if they are low SNe II noise and not very, very nice for type 2, but you can use them. So you can increase your sample. As I mentioned, people are working on ZTF on this. And otherwise, you have the other method that I show you also, the photospec collimated method, sorry, that use only the light curve, and this with ZTF will be easy to obtain.
Thank you.
You're welcome.
Thank you. Adam?
Thomas, very nice talk. I apologize, I didn't catch all of it, but I'm familiar with your work.
Yes.
Do you have the slide where you showed the different calibrators that you used?
Sorry, this one?
No, where you label the different objects, the different type 2 calibrators.
Not sure which one you mentioned. No.
You know, which are TRGB, which are Cepheids, and the one that's 4258.
This one? This?
No, it's a plot where you show them individually in your paper.
I don't have it on slide here. Sorry.
Okay. I don't know if it's shown here. I thought it was interesting. Just something I would point out to people is that you know, you have some calibrators that use tip of the red giant branch and some that use Cepheids. But there was one I was so intrigued by because it's a supernova in NGC 4258.
Yeah.
So it doesn't use either Cepheid. There it is. This is the plot I was looking for. So in black are the calibrators of type 2 supernovae from Cepheids. In red are TRGB. I love the blue point because that one is type 2 supernova in NGC 4258. So it uses neither. It's a 2-rung distance ladder essentially with that one. And boy, it'd be nice to have more of those.
Yeah, it'd be nice. But yeah, I remember that we talked about this point. We're trying to use only a 2-rung distance ladder, but I wasn't able to derive.
I mean, it's obviously consistent with the red and black points, but
they are large, yeah.
But it has large errors, yeah.
They were large because I think the velocities estimation were large, if I remember well about our discussion. But yeah, if we can find more of this, it would be very nice too for the future of type 2s.
Okay, thank you. Any other questions or comments? So I think we can thank Thomas again. Thank you so much.
Thank you very much for that attention and the invitation.